In 1.11, we are defining continuity at a point. This is a formal definition. When you see a graph, you can normally just tell if it's continuous by looking at it. So I'm going to draw a random graph here, and maybe there's something like this. Okay, if I want to prove that it is actually continuous at some point C, let me just go like this. Let's make this C. Okay, there's a couple qualifications that have to be met. Okay, the first thing is there has to actually be a point at C, so this point needs to exist. So the first condition, f of C must exist. Can't be a hole there or anything like that. Okay, the next thing is that the limit as x approaches C must also exist. Okay, and then the last condition is the limit needs to approach as x approaches C, and the value of f of C must actually be the exact same thing for the graph to continuously move through that point. So the limit as x approaches C of f of x needs to actually equal to f of C. Okay, so for this given function here, let's prove that it is continuous at the given x values, or show whether it is or not, using the qualifications from above. So the first thing is f of C has to exist. So for A, it's at x equals -1. So let's make sure that f of -1 actually exists. So step one, what is f of -1? If x equals -1, that would be this function. So that's -1 plus 2, which is 1. Okay, now we have to also show that the limit as x approaches -1 exists. So let's define the limit. Okay, the limit as x approaches -1. Let's look at this. Well, -1 is actually a point where the piecewise function connects its two pieces. So we need to consider it from both the negative and positive direction. So if I come from the negative direction, then I'm a little bit less than -1. So I'm plugging into this function right here, which is -1 squared. 1 plus 2 plus 1, which is 4. Okay, let's try to find the limit as x approaches -1 from the positive side, which is going to be a little higher than -1, which is going to be in this expression. So -1 plus 2, which is 1. Okay, so we have a problem right here because the limit as x approaches -1 does not exist, because in one direction it is 1, and in the other direction it should be equaling to 4. Okay, so since the limit as x approaches -1 does not exist, we can prove that f of x is not continuous. At x equals -1, and the reason is because the limit as x approaches -1 of f of x does not exist. Okay, let's go ahead and consider x equals 2 and see if it works for x equals 2. So first let me calculate f of 2 to make sure it exists. Okay, when x is equal to 2, I'm using this function. So 2 squared is 4. Okay, now let's consider the limit as x approaches 2. Well, 2 is where these two pieces of the graph are connecting, so I do need to check from the left and the right because it's not continuous there, or I don't know if it's continuous there. Okay, from the negative side, I'm doing x plus 2. 2 plus 2 is 4. If I come from the positive side, I'm using 2 to the x, so 2 squared is 4. So the limit as x approaches 2 does in fact exist. Okay, so now I know the limit of x approaches 2 exists, and I know it equals to 4. So the last condition I need to meet is that the f of 2 needs to equal the limit as x approaches 2, which it does, because the limit as x approaches 2 of f of x is 4. F of 2 is actually 4. So the third requirement is that f of 2 is equal to the limit as x approaches 2 of f of x. So in conclusion, f of x is continuous, because the limit as x approaches 2 of f of x is equal to f of 2. And if they're equal, then they also must exist. Okay, for the next examples, we are going to identify the type of discontinuities, if any, and where they occur. So we're checking to see if it's continuous, and if it's not continuous, what kind of discontinuity is there. Okay, so if I look at this piecewise function, they connected x is 4, so that's going to be the only point that's an issue. Both of these are continuous at every other point in the domain. So let me check at x equals 4. At x equals 4, from the negative side, that would be 3 times 4 plus 1, which is 13. If I approach x, as x approaches 4 from the positive side, I'm using this other function, so 4 over 2, which is 2, and then I subtract 1. Okay, so this is not continuous because the limit doesn't exist. So there is a discontinuity. What kind of discontinuity is it? Well, it goes from y is 13 all the way to y is 1. So this is going to be a jump discontinuity. And where does it exist at? At x equals 4, because that was the only possible place for a discontinuity in this function. Okay, let's go ahead and do the same thing for the next one. Okay, let's consider first the limit as x approaches, let's see, there's no domain issue, so it's just x equals -1 that I'm concerned about. So as x is approaching -1 from the negative side, I would be using this function. So let's consider that first. -1 squared is 1, minus 2, minus 1, which is -2. If I approach -1 from the positive side, I'm using this function, which means -1 minus 1 is -2. So the limit as x approaches -1 is -2, which is a good sign. Okay, now what actually happens at x equals -1? Well, at x equals -1, this is g, not f. At x equals -1 on the function g, it actually is equal to 5. So the limit exists and it's approaching -2. However, at the actual point, it's equal to 5. So this is a discontinuity. What kind of discontinuity is? It's going to be a hole. And where does it occur? At x equals -1. And I'm going to sketch a quick picture so you can see. Let's see, at x equals -1, let's see, the limit is approaching -2, but the actual point's at 5. So the actual point's up here somewhere. The limit is actually way down here. So if I were to sketch it, it might look something like that. I can see from the picture there is a hole there. Okay, the last example, we're going to try to figure out what value of k will make this function continuous, and the only point I'm really concerned about is x equals -2. Yeah, let's consider one more example regarding continuity. So this is h of x. It's 2 minus x squared when x is less than or equal to -2. It's 4x plus k when x is greater than -2. You're trying to determine what value of k will make h continuous. So I kind of still need to consider all the previous qualifications, but I need to turn it into an equation. Let's see. Now at f of -2, what is that going to be? 2 minus 4, -2. Because as x is approaching -2 from the left side, it's also where it's going to equal -2. I know that it's going to exist at the same place as the left-sided limit. Okay, so to make this true, I need to make sure that at x equals -2 from the left side and the right side, they were equal to each other. So I'm going to set them equal to each other. So I'm really saying that at -2, the left side needs to equal to the right side, and I'm plugging in -2 for x because that's the point I want to make this true at. So 2 minus 4 is -2, -8 plus k, so k would have to be 6 for this function to be continuous.